evening, guys. So today we are going to discuss about the primer design. Okay, so we have come up with three primer pairs where all these primer pairs will bind to the E. coli sequence, the E. coli gene sequence, and we have come up with three types of gene from the E. coli. And here we have the first one. We have the trilby gene sequence from the E. coli, which I have sourced from the NCBI, and the length of the trilby gene sequence is around 900 plus base pair, and um, the yellow highlighted sequence over here it is a forward primer, and the reverse primer will binds to the blue highlighted sequence over here. So for the forward primer, we have this sequence. It is around 20 base pair, and we have uh, reverse primer over here. It is also around 20 base pair. And if we look into the melting temperature, is around 60 degrees Celsius, and the forward primer GC content in terms of the in percentage, it is 60%, and the length is 20, as I mentioned. And yeah, this is a little bit of the information for the forward primer. And for the reverse primer, it is also 20 base pair, and the melting temperature is also the same as the forward primer. And the product length from the yellow sequence to the blue sequence over here is around 76 base pair. And for your information over here, the FASTA sequence from the NCBI, it provides the sense strand of the cDNA. So basically for the forward primer sequence, it is basically the same. We just copy and paste over here, so it is basically the same sequence. And for the reverse primer, it is the reverse complement, which means that it is complement to the sequence over here, but it is in a reverse orientation. As you can see over here, GACGC. Okay, so the complementary sequence is going to be CTG, CG. So it is in a reverse orientation, CG. Okay, so this is basically the reverse primer where it will bind to the strand of the DNA template. Okay, so the product length 76 base pair, and this is the overview of the annealing of the primer, and also the amplification of the trilby gene in the E. coli. And as you can see over here, the forward primer binds to the position 93rd to 112 base pair, and it starts to amplify from the 93 to the end of the 3' to the 3' end over here, which is at the 168 position. So the length is from 93 to 168, and the length of the final PCR product will be 76 base pair. Okay, move on to a little bit of a brief discussion for the primer design. And for the forward primer over here, the primer length 20 base pair, and the annealing temperature we just have to subtract by 5. We minus the melting temperature by 5, so we got 55, around 55 degrees Celsius. And the GC content in percentage, we have around 60%, which is quite high, and we want the GC content to be as high as possible, but not too high, because we want the primer to have a stable annealing at the template, so that it won't wear off during the PCR reaction. And also we look into the stability of the 5' end and 3' end of the primer when it binds to the template. So at the 5' end, the sequence at the 5' end, the GCTCGG is quite high in the GC content, because you can see a lot of G and C at the 5' end. So this is actually ideal, because it enhances the ability, it enhances the stability of the binding at the 5' end at the template. So this enhances the stability of the annealing, and also but it is not important. We don't have to prioritize the 5' end, because this is not the starting point of extension. The tag polymerase will not bind to the 5' end and begin extension process, but instead it binds to the 3' end. So we don't have to prioritize much on the composition of the nucleotide at the 5' end of the forward primer. And another factor that we look into is the GC long run. So we have to make sure that the 5' end don't have the GC long run, not only the 5' end but also at the 3' end as well. We don't have this to occur. They don't want the GC long run to occur at both ends. So if they have the GC long run, it can increase the risk of the primer dimer formation, where the primers will bind to each other. It's either in between the forward and forward primer or the forward and reverse primer, or sometimes it can form the hairpin structure where it can have the self-complementarity. Yeah, so this is not favorable for a primer design. Okay, so not only the formation of primer dimer and also the hairpin structure, it can also form the secondary annealing, which is the non-specific binding of the primer to a non-specific position of the gene of the template. So this is not favorable as well. So overall, the sequence is stable and acceptable because there's no GC long run, and the GC content is acceptable within the acceptable range, and it forms a stable binding, a stable annealing process. So yeah, the forward primer is stable. And if we look into the 3' end of the primer, yeah, as I mentioned, it don't have a GC long run, the first factor. And the second factor is that we have the GC clamp at the end of the 3' end, the second criteria. So it is a good 3' end we have designed. And yeah, it is important because the Taq polymerase will bind to the 3' end to begin the extension process. So they have the GC clamp, which means that the stable binding of the primer will occur, and the Taq polymerase can extend much more efficiently to form more and more DNA strand. And overall, the 5' end and 3' end, the forward primer is well designed. So yeah, we have to. So we move on to the reverse primer. Okay, so the reverse primer, we have the same primer length, which is 20 base pair, and the GC content is around 55%, and it takes up around 11 out of 20 of the GC content. And if we look into the stability at the 5' and the 3' end, the 5' end of the primer, it is much lower in terms of the GC content as compared to the forward primer. And yeah, it has a weaker binding strength as compared to the forward primer. But as I mentioned, it doesn't have to be prioritized much because that is not the point where the Taq polymerase will bind and extend the DNA, so we don't have to look into it. And there's no GC long run. As long as it has no GC long run, it forms a stable binding at the template, and yeah, it is acceptable to be a good 5' end of the reverse primer. And for the 3' end of the reverse primer, there's a GC clamp, and there's no GC long run, and the GC content is acceptable. There's a good amount of GC in at the 3' end, and yeah, it is stable and it is ideal for the extension. So overall, for the reverse primer and the forward primer, they form a good primer pair. Why? Because if we look into the difference in the melting temperature, okay, this is the final criteria where the primer pair have to achieve, because the difference in the melting temperature should not be more than 3 degrees. Because if it is more than 3 degrees, we can say that they are not compatible with each other. Okay, so if we look into the melting temperature, both are actually having the same melting temperature. The difference is literally 0 degree. Okay, so it is a good difference, which means they are compatible to form a good primer pair. And if we use the Wallace rule to calculate the difference in the melting temperature, this is just a rough approximation. The difference in the melting temperature is around 2 degrees Celsius. So yeah, it is still not more than 3 degrees Celsius. And this primer pair is a very good pair, and it is said to be ready to be used for the extension, the PCR of the TROB gene sequence. Okay, so we move on to the next gene sequence in E. coli, which is the RAC-A sequence.
Okay, I will be explaining about the REC-A gene sequence. Okay, as you can see, this is the gene sequence from the NCBI database. Actually, the highlighted part of my forward and reverse sequence, I don't know where it went. Okay, so moving on. This is the forward primer sequence that starts from 5' to 3' N as usual. And the temperature is also plus, and it has the ideal primer length, which is 20, and it's good because it's in the range of 18 to 30, and 20 is the very ideal number. And then as we can see at the forward primer start and forward primer stop is actually a very is a large number because this is a very large primer, so that's why it start and end a very in a huge values. Okay, and the melting temperature is 59.97, and the GC percent is 55, which is very ideal, not more than 60%. And the primer self-complementary is also okay, which is 3, and self-3' complementary is low, which is also ideal in choosing primer. Okay, so that is the reverse primer, which is this one, the highlighted in blue. And then, Joel bawah sikit. Okay. So it's also have the same complementary length with the forward primer, which is 20, and the reverse, melting temperature is also 59.97, which is also the same and complementary with the forward, and have the same value of GC percentage, and a high reverse self-complementarity of 5, which is what we want, and a low self-3' complementary T, which is 2. The problems comes here when it comes to the product length, which is 866. We can see in figure 2. Can you move downwards a bit? Okay, you can see in figure 2, the primer itself is very, very long compared to figure 1 on Joel's explanation. And this is because of the product length of 866. I know this is not an ideal primer, but we're just going to show what an ideal and not non-ideal primer is. Okay, so for discussion, yeah, this is also the same with what Joel had mentioned before. And then we move on to the annealing temperature is 54.97, and the GC content, as I mentioned, is 55%, which is nice. And this confirms that the GC content is ideal and fall within the optimal range. Okay, to start with the stability of the 5' and 3' N. The 5' N, as you can see, start with CTGCTA. This part is not critical as stack polymerase does not start extension from 5' N, and it is start from 3' N, 3' N instead. And it also has high GC content, which is very, you can say, important for to support the primer stability. And this 5' N of the forward part is actually considered acceptable and actually well designed. For the 3' N, ATCA is the most crucial part for initiating the DNA synthesis, but it lacks a strong GC clamp, as Joel had mentioned, because it needs to bind but it lacks GC clamp, so it's not that really stable and acceptable, but it's still okay lah. You can still use it. Okay, moving on to the reverse primer. It also have the same temperature, primer length, and GC content as the forward primer, which is, as I said, suitable and complementary with each other. And the 5' N of GGC-GGG. This is not critical for extension, but we can see here from the GGC-GGG is contains a long run of a single base, which is GC long run. And this could lead to instability of the primer itself, because it could lead to because the structure will not be as stable and it's not really acceptable. Okay, so the 3' M is also same, since this is critical for tech polymerase, is also same with the forward 3' N, which is lacking GC clamp, and also have a low, both of forward and the reverse primer have low self 3' complementary score of 2 that confirm the low risk of forming stable and primer dimer. and making it stable for specific extension, but it still lacks GC clamp and has a lot of GC long run. So in conclusion, this primer rack A, based on the analysis, but this primer is not considered as ideal, especially for PCR, and the predicted product of 866 base pair, which is very very long, can significantly um which is actually the ideal base pair for a good primer is actually just a long 70 to 200 pp, just like what Joel's primer is. And this very very long primer length can lead to a longer amplification efficiency, meaning more the results would be more rate, and it's not going to be a apa tu, tak tepat. Okay, it will be contaminated ke apa-apa ke macam tu lah. Okay. And it's also generally harder to optimize because it's a very such a long primer, so it's hard to optimize. You have to change this, have to change that, and the results will not be as good. And the assay of the PCR later will be less robust for quantitative measurement. So it's not, dia tak tepat, tak jitu. Okay. And so in conclusion, this primer is not ready to be used for PCR for reg aging. So I'm just showing the non-acceptable kind of primer, unlike my other two group mates. Okay, thank you.
Okay, so we move on to the last E. coli gene sequence, which is I choose ADK gene sequence. The full name of ADK is adenylate kinase. And as you guys can see, the yellow highlighted one is forward primer sequence from 5' to 3', and the blue highlighted one is the reverse primer sequence. So firstly, for the forward primer sequence, its template strand is plus and its primer length is 20, which is an ideal length. Actually the ideal length is from 16 to 30. So 20 is within those ideal range. So it is ideal. And the forward primer start at 275 and stop at 297. And its melting temperature is 59.998 degrees Celsius. And for the GC content for forward primer is 55. And then for self complementarity is 4, and its self 3' complementarity is 2, which is low and stable. And then move on to the reverse primer sequence. Actually, it is the reverse complement of sense strand, not the actual reverse primer, because like Joel had mentioned, because the reverse primer binds to the anti-sense strand. So we see its reverse complement sequence in the sense strand, not the primer sequence itself. So we only see the reverse complement in the sequence. So and then the template strand for reverse primer is minus, its primer length is 20, same like the forward primer, and it start at 365 and stop at 346. And for the melting temperature is 59.97 degrees Celsius, and its GC content is 55, which is ideal, and self complementarity is 4, its self 3' complementarity is 3, which is also considered low and ideal. So the total length of the product is 88. And as you guys can see, for the figure 3 is an overview of primer, annealing, and amplification on ADK gene. So at the left side is the forward primer, which is matches the sequence of sense strand at position from 278 from 278 until 297, and the at the right side is a reverse primer sequence of sense strand at position 346 until 365, and the total length for PCR product will be 88 base pair. And then move on to the discussion. This also same like what my teammates had mentioned about their annealing temperature, primer length. So for forward primer, its annealing temperature is 54.98. How do I get this temperature? I just minus the melting temperature, minus with 5 degrees Celsius. And then its primer length is 20 base pair and its GC content is 55%, which is ideal within the recommended GC content, 40 to 60%. And then for the stability of 5 prime and 3 prime and 4 forward primer, the 5 prime of forward primer is like CAGAC. It is not critical for DNA synthesis as DNA polymerase does not initiate extension from the 5 prime and instead it's initiate at 3 prime end. And at this region, it has moderate GC content, which helps maintain overall primer stability, and therefore the 5' end is considered acceptable, while at 3' end of forward primer, which is GCG, is the most important region for initiating DNA synthesis. And at this end, it contains GC rich sequence, and then it's forming GC clamp that improves primer building to the template DNA, and it also enhances the efficient extension by DNA polymerase. And then the primer also has low self-complementarity at the 3' end, which reduces the risk of primer dimer formation. So overall, the 3' end is considered stable and suitable for PCR. So both 5' and 3' and for forward primer is acceptable and suitable for PCR. And then move on to the reverse primer, which is the blue highlighted one. And then its annealing temperature is 97 degrees Celsius, almost closely same like forward primer, and its primer length is 20, same like the forward primer. And then move on to the stability of 5' end and 3' end. Okay, for the 5' end of reverse primer is CCGAC. So CCGAC is a sequence of reverse primer. The blue highlighted one is the reverse complement. So it's not same. But I forgot to include the reverse primer sequence. So I just tulis dekat dalam point tu. Okay, so that sequence CCGAC at 5' end or 5' end of reverse primer is not critical for DNA synthesis since DNA polymerase extended only from the 3' end, and their GC content is relatively high at that region, but it does not interfere with PCR performance. So the 5' end is considered acceptable, while their 3' end, which is CGAT, is the most important region for initiating DNA synthesis. At that region, it contains GC base that provide sufficient binding stability. And although the GC clamp is weaker compared to the forward primer, the reverse primer shows low self 3' complementarity. So it has low risk of primer dimer and acceptable at 3' end. So same like the forward primer, the reverse primer also acceptable at both 5' end and 3' end. So overall, I consider this ADK gene to be an ideal target for PCR because it is a housekeeping gene that involved in energy metabolism, meaning that it is really essential and conserved in E. coli. So this make it a reliable and stable gene for amplification. So and then apa lagi? In addition, the primers that I designed, not me, but NCBI database design, have optimal properties, including appropriate length, balanced GC content, similar melting temperatures, and stable 3' ends. So altogether, all of these factors support efficient, specific, and reproducible PCR amplification. So overall, this gene is an ideal for Ecolite primer. That's all from me. Thank you.
Okay, so that's all from group 10. We have been presenting two acceptable primer, which is THRB and apa namanya?
ADK. ADK.
IDK gene, and one non-acceptable primer, which is mine, which is rec A. Okay, so that's all from us. Thank you.